So continuing here, what do we have? We know from the 68.95, 99.7 rule that we have 95% of the data is in between two standard deviations. That's what we know. So in class, when we get over our sample mean happened to be, let's say it was 1,050. Okay, and then we would say, we'll say our standard deviation was 14.1, we would add that and subtract that to both. And that would be the upper limit and lower limit of 95% of the data. That's what that means. Okay, so whatever x bar happens to be, we'll either subtract 14.1 or add 14.1, and that'll contain approximately 95% of all our samples. That's what that says. So 95% of the time, if we do this procedure, we're going to capture the true population parameter. That's what that means. We have to be really careful when we read these problems here. They're talking about confidence intervals. That means that if we repeat this process about the same way, about 95% of the intervals will contain the true population parameter, which we're trying to find through all our sampling. So in this example right here, it says, so that means if we did this many times, 95% of the intervals that we would do would contain the true parameter. So it doesn't mean 95% of the population lies in that interval. This is not true right here, okay? So let's look at an example. Example 1 says a poll of 1,500 men were polled and asked about what percent of the time they watch at least one football game per week, and about 64% said they saw at least one game per week. Now the poll announced a margin of error of 3 percentage points. So margin of error of 95%. That means that it's already taken into account the standard deviation and the sample size. We're just saying that the margin of error meaning your two standard deviations to the right, your two standard deviations to the left, is already computed to be 3%. And that's why we only add 3% once and take away 3% once, because the margin of error includes the sample size and the sample standard deviation. So we say that we're 95% sure that the true percentage of American men watching NFL games at least once per week is somewhere between 61 and 67%. Again, the margin of error already computes the standard deviation and takes into account the sample size. Likewise, here we have a simple random sample of 150 customers going to a gas station. The average is 8.4 gallons, and a margin of error, again, margin of error, MOE, 2.15 gallons for 95% confidence already includes standard deviation and sample size. So all we're simply doing is adding 2.5, adding the margin of error to 8.4 and subtracting 2.5 from 8.4, and we're getting this confidence interval. So 95% sure that the true amount of gallons per gas, true amount of average of gallons pumped will be somewhere between 6.25 and 10.55 gallons. Now let's take a look at the price of a 2-liter bottle of Pepsi. Well, the sample standard deviation is 23.4. That's given, a random sample of 50 bottles, and the average price was $1.64. So since we're given this information, we're asked for a 95% confidence interval. We take 0.234, that's our standard deviation for the population, and we divide by the square root of 50, because that's our sample size, and we get, we divide that out, and we multiply it times 2, because that's going to be our margin of error, because it's 95%, so we need two standard deviations right there. Okay, so then we add 0.066 to 1.64, and we subtract that, and we get 1.57, and so our interval is 1.57 to 1.71. That is that we are 95% sure that the true average price of a 2-liter bottle of Pepsi is between $1.57 and $1.71. So we're 95% sure the true average is somewhere between those two prices. That's what we just said. Okay. Now our confidence interval size does not have to be 95%. It could be 90%, it could be 99%, it could be 95%. So just notice the pattern here, that as my confidence interval increases from 90 to 95 to 99, okay, our interval increases in size. And it makes sense because we are less confident of a smaller target, because we're saying 90% of the time the true parameter of gallons of gasoline will be between 7 gallons and 9.8. You see how the margin increases in size with the increased confidence. So as we get more confident, our um, our interval is going to get larger. Okay, so we're more confident of fitting a larger gap. To see how we have a greater range to have the population average number of gallons of gas fall in there. Okay. So the official definition of a confidence interval, let's say 90, 95, 99, is that we are that confident, 90%, 95%, 99% confident that the true parameter, in this case the average number of gallons of gasoline, computed from our sample data, like when we took our sample data, that the probability, it has a probability, like a 90% probability, 95% probability of producing an interval that contains the true parameter. That means that we're that confident that our sample interval is going to contain the true parameter. That's what a confidence interval says. So you might be wondering how we computed those intervals. Well, we take our x bar, as we said before, there's our x bar, and since we're assuming normality from the central limit theorem, what that's saying is now what we can do, we take our x bar right here, we take these with this z star, that's a critical value, that's a table that's in the back of our book, okay, in the blue book, or the table of standard normal values. We could also do it on our calculator. So that basically means that we take the standard deviation for the population, divide it by the square root of the sample size, and multiply it times the critical value. So for a 95% interval, remember how we said the two standard deviations to the right and two standard deviations to the left? Well, remember that 2 is approximate. It's 1.96 technically. So we take 1.96, multiply it times the population standard deviation, and divide by the square root of the sample size, and if we don't have sigma, we would use S. Okay, so whatever data that we have, that's how we'd compute the margin of error. So this whole thing put together, the amount that we add and subtract to the x bar, that is the margin of error. So this z bar times sigma over square root of n, that is the margin of error. So we looked at some teachers from Philadelphia. We found out that 180 teachers were 155 return surveys, and what we found out that the average number of years of teaching of these teachers was 13.6, and we assume that the population standard deviation was 7.3. And what do we want to know? We want to know a 95% confidence interval of the true average of years of experience of a teacher in Philadelphia. Well, since the average was 13 point, that says 13.6. Okay, so let's say that's 13.3. I don't know why this is 13.6. Let's say it's 13.3. If that's 13.3, then we're going to use 1.96 because that's the number of standard deviations to get 95% confidence interval. That's in our table in our book, or we know that the 95 rule. There's sigma right there, and there's the square root of 155 right there. So we're 95% sure that the true average of years of experience is between 12.15 and 14.45 years of experience. Now, likewise, when we do a 90% confidence interval, our critical value is smaller. Again, look in the back of the book or look it up on the table online. Any of the resources I've shared with you, and you'll see it's 1.645. That's the critical value for a 90% confidence interval. And notice that our interval is going to be smaller. So we have a smaller range with a lower confidence. So again, if we make that picture, that normal picture here, so we're coming in here, and we have 1, we have 2, and remember this picture, okay? It's the number of standard deviations to the left and to the right of the mean. So 99% confidence interval, our critical value here is 2.576. Again, the range is going to be larger, okay, because we have a larger, we're more confident, we're 99% confident, more confident of having of the true parameter being in a larger range, and that kind of makes sense conceptually. So the answer to part A, what does it explain in words? A 90% confidence interval in this situation. What does that mean? That means that we're 95% confident that the true average years of service, years of experience of Philadelphia teachers is somewhere between 12.15 and 14.45 years of service. That's what this information means after we calculate it. That's the whole reason why we do it. So this example with the McDonald's coupons, just to show you that you could have a confidence interval that's not 90 or 95 or 99. You could also have 98. Again, you look up the value. We have all kinds of confidence intervals. We could have 97, 96, and we see that's going to be 2.326, and that makes sense because it's in between 1.96 and 2.576. That makes sense. And so we make our margin of error. We find out what it is, and we subtract it to 82.73 because that information was given. That's a number of fries in a medium container of fries. Okay, that's all that one was. So the general formula is right here. We have x bar is equal to plus or minus z, which is the critical value, the normal critical value in the back of our table, okay, times sigma over square root of n. So basic thing we have to remember is that this assumes we have a simple random sample. If we don't take simple random samples, then this data is not going to be as accurate as we hope it would be. And we should have a sample size that's reasonable. It should be like 20 or above, as we keep saying. It's not always possible, but that's what we want to shoot for. I almost skipped over this part right here. That's when we have a margin of error that we want to stay between. So let's say we want to have a margin of error of plus or minus. Remember the earlier problem was 3% for the NFL. Now, in order to get to a desired margin of error, a MO, okay, in order to set this margin of error, we have to work backwards in order to solve the problem. So basically, the only factor that we can control is controlling the sample size. So basically, what they're saying is, let's just say we want to have 95% confidence. That's going to dictate our z. That's going to dictate the z. We have to have sample standard deviation of some type. Okay, the French fries, we have to have this already. Okay, so this n right here. Okay, so this this m right here, we want to figure it out by changing m. Okay, so we have to use algebraic manipulation. So in this case, we put in 1.96 because it's 95% right here. Okay, we want to stay at a margin of error of 0.75 or less. We put that right here. Done. Then the sample standard deviation that was given in the earlier McDonald's problem above, that would be given to you. You put that here. So we have to use some algebra to try to determine what value for the square root of n is going to work so that this inequality holds true. And if you do that, you'll get a decimal answer, and you have to round up to get to the next highest sample number. So you can't have a sample of 120.473, so you go to 121 in this case. All right, there you go. So it's algebraic. It's using this formula backwards in order to find n, okay, by putting in a fixed margin of error.